Okay, so let's finish up this second lesson of chapter 1, and we are at example number 3, and we're asked to write the equation of a transformed function. So here's our parent function. This is the one that we're starting with, one that we should be fairly familiar with, and now we're wondering what g of x is going to be, and we're going to define this in terms of f of x. So we're going to have, f of x. But we're going to add something to it, so I'm leaving some spaces. I guess there's two options, right? We could be putting an a value, some value out there, or we could put in some b value out there. Let's just see what we're going to do. Here's a table. We can make a table of values. So looking at all my x values of my parent function, so this is the f of x, negative 12, negative 8. Here I'll give myself a little bit of space, negative 12, negative 8, and I think it's going by 4s, negative 4, 0, 4, 8, 12. And what happens is these vertical lines mean absolute value. So if there's a negative value, it makes it positive. So here I get 12, 8, 4, 0, 4, 8, and then 12 again. Okay, so that's the first part. And now let's take a look at my new function, g of x. So my negative 12, I don't really see one, do I? But if I go to negative 4, so when x is negative 4, what's my y value? Now it's all the way up to 12. So at negative 4, here I can put a 12. At 0, I get a 0 again. At 4, here I get a 12. What would I get at 8? So 8, it's kind of hard to see because it's still going up. But I think if I look for this pattern, this value here is getting multiplied times 3. So if I was to multiply 8 times 3, I would get 24. Does that look like it's about right? So this is 16, 18, 20. So 24 would be about another square up. Yeah, right about there, wouldn't it, right? So that looks like that would be good. Negative 8, comma 24. So really what I'm doing here is I'm taking this value here and I'm multiplying it by 3. So my x value, so in any point in my original x comma y, it's getting mapped onto, the x is staying the same and the y is getting multiplied times 3. So going back over here to my definition of g of x, I'll write out the A and the F and all this kind of stuff. Okay, so what do these different letters do? The A multiplies my y values, and the B, 1 over B is multiplies the x values. So when looking back here, my x, the way I've written it hasn't changed. My y's got multiplied times 3. So in other words, I want to say that A is equal to 3, and since x isn't getting multiplied by anything, B is equal to 1. So the way I'm going to write this, maybe I'll make it blue because it looks better, nice and big, g of x is going to be equal to 3 times f of x. Okay, now let's go on to the next one. So now it's pretty clear that it's going to be a reflection over the x-axis. So again, I like my kind of wet ink analogy. So if you think about the original line as being painted with maybe wet paint even, and then we fold across this x-axis. If you can imagine taking the paper and actually just sort of folding it over, this is where the image would get. And so when we reflect over the x-axis, what that really means is that we are multiplying the y values by negative 1. And it might seem kind of contrary to think if you're reflecting over the x-axis that you're multiplying the y values by negative 1. But if we go through the work again of making this table, I think you'll see how it works. So maybe I'll pick 0 over here and I'll go negative 1, negative 2, negative 3, 1, 2, 3. So those will be my x values. So 0 goes with 0, because here's 0, 0. 1 for my x would be equal to 1 for my y. This goes along here, and again this is absolute value, so I get 1, 2, and 3. So that's my original function. Now, so looking at my image function, g of x I'm going to do in green. G of x, 0 is 0 still, so here's the x value for my g function, here's my y value. When I put a 1 in for x, for this function I get a negative 1. So when I put a 1 in, I get a negative 1. A 2, I get a negative 2. And so on. And what about when I go negative? When I go negative, I get negative 1, negative 2, negative 3. So now I can say, okay, if my x values are staying the same, what's happening to my y values? My y values are getting multiplied by negative 1. So just again, a reminder of how this works is that my a value out here multiplies my y's, and the reciprocal of my b value multiplies my x. So if it is a reflection, then we're going to get y is equal to negative f of x. Okay, so this is how I would define it in terms of f of x. I could also write it as y is equal to negative the absolute value of x, because that's what f of x is, right? It is equal to the absolute value of x. So depending on how the question was asked, let's just see what the question says. Write the equation of a transformed function. So it didn't say in terms of f of x or not. So it's a little bit ambiguous. Those would be both would be proper ways of doing it. Okay, here we have another one. And we don't have to do a table of values in this one. So if f of x is our original function, what's happening to our g of x values here? So let's take a couple of points. So here we got, if I say f of x, and then here is g of x. F of x we have 0, 0, and g of x I have 0, 0 as well, so that's the common point, right? How about f of x when I do 2, here's an easy one to figure out, 2, 4, and now I kind of have a choice here. I can either think of this as a vertical stretch. So if you imagine a vertical stretch, that means that this point here would correspond with that point over there. Okay, so let's think about this as a vertical stretch first of all. Thus my corresponding point with 2, 4 would be 2, 16. And if I picked, maybe I pick 1. 1 would go originally, it looks to me, with 1. Can I make some space here? Let's try something fancy. Can I go and take this and just move it down? Mostly successful, hey? I just have to erase this. Put that. Okay, so I'm going to add another one inside of here. For my original function, this looks like 1 here, and it looks like it lands right there, and that would also be 1, so 1, 1. If I'm thinking of this as a vertical stretch, and it's got stretched upwards, that would be at 1, 4. Okay, so what's the pattern that we see? Seems to me when we think of this as a vertical stretch, my x values are the same, and my y values are getting multiplied times 4. So if my original function is x, y, the corresponding points here will be x, 4y. Okay, and you'll recall how that works then. I could say that g of x is equal to, here are the two kind of functions that we're working with. This one here multiplies the a value, and the x values are multiplied by the reciprocal of b. So in this question, if the y values are being multiplied by 4, that means my a must be 4. So I'll go like this, and I'll say it's a 4 here. Since my x values are not being multiplied at all, I can just erase those. Oh, how come I'm not getting any erasing here? There we go. So I could just write g of x is equal to 4 times f of x. I could also write it as g of x is equal to 4 times x squared. Okay, so that's the first way of looking at it as a vertical stretch. I could actually also look at it, and sometimes you can do more than one transformation, and you'll get the same result. So if I erase this work here to begin with, I'll try to erase it. If I erase this work here, and instead of a vertical stretch, I could think of this as a horizontal compression. So if this was my original point, I can think of it as horizontally it's getting compressed, it's getting pushed inwards like that. So if my original point on f of x is 2 comma 4, my corresponding point would be over here, would be 1 comma 4. All right, if my original piece here would be, here's another nice one, 4 comma 16 on f of x, then on g of x it would be 2 comma 16. So thinking of this as a horizontal compression, now my y values are staying the same, but what's happening to my x values? My x values are being halved. Okay, so if I say x comma y is my original function, then for my corresponding points I'm going to get x over 2 comma y. Okay, so here thinking about my g of x is equal to some a f of b of x. Okay, so you'll recall that a is whatever the y value is being multiplied by. It's not being multiplied by anything. So this a value can just be 1, or I can just erase it if it's a 1. You remember how this works now. The b values are being multiplied by, or the x values are multiplied by 1 over b. So what are the x values being multiplied? X is multiplied by 1 over 2. So therefore b is equal to 2. So I can go over here and I can say that, oh, try this again, this b value is going to be equal to 2. Okay, so both of those ways of looking at it are the same. So here we could say g of x is going to be equal to f of 2 of x. Or I could say g of x is equal to, now we have to go inside the function of x squared, so we say 2x all squared. And you see how mathematically these are identical, right? So inside the function, because our original function is y is equal to x squared, if my b value would also get squared just like x does, wherever I see an x I replace it with bx, with 2x in this case. So this would be a horizontal compression because that 2 is inside of there, and this is a vertical stretch. And you'll see that both, if you imagine either pushing this inwards like that, you can take f of x and turn it into g of x, or I can take each point and vertically stretch it and it comes out the same. Let's do our summary here for all these transformations. So if we have a negative sign out there, that transformation is, this is a reflection. And it's a reflection over the x-axis. Okay, and how's the mapping look? If we start off with x comma y, then we're going to end up with x comma negative y. So an example here would be if we had a graph that the original function, say, looks like this, then my reflection is going to look like this. Oh, I was trying to do red on that one. Let's try it again. My reflection would look like that. Okay, so for the next one, if the negative is inside of here, it's going to be a reflection, can't spell, a reflection over the y-axis. And how does it work? well, if x comma y is our original function, the x's get multiplied by -1, so it looks like negative x comma y. What would be an example of this? Let's do a shape maybe. Let's say if the shape looked like this and then went like that, a reflection over the y-axis. So here's the y-axis. My reflection would end up looking like kind of like that. All right, so over here my my a value. So this is multiplying the y values. So it's a vertical. Now it's either a stretch or a compression. So it's a stretch when a is greater than 1, and it is a compression when the absolute value of a is less than 1. Okay, and so how that works is if x comma y is our original, then we get ax comma y. We multiply, oh sorry, did I do that right? No, I did not. We multiply the y values, not the x values. Let's try this again. X comma ay. And what would that look like? So if we start with a shape, oh I don't know, let's start with a shape that looks like this. And now if we stretch it vertically, everything gets stretched vertically, so it would start higher up. This line should be a little bit steeper. Oh boy, okay. And let's see if I can just erase only the little red part here. Okay, so this would go like this. Kind of like that. So everything gets stretched vertically. Our last one is our b value, and this is a horizontal change, so I'll say it's a horizontal. And in this case, our x values are multiplied by 1 over b. So this whole stretch and compression kind of works the opposite way. So the stretch, it's a stretch when the absolute value of b is smaller, right? Because here where the x values are multiplied by 1 over b. So when b is a small number, say if we put a 0.2 in there or something, then your 1 over 0.2 is just, that's the same thing as multiplying, say, times 5. So when the absolute value is less than 1, then the x values get larger, and that's a stretch. When you get a compression is when the absolute value of b is greater than 1, because then you're dividing by 1 over something bigger than 1, and you're making the x values get smaller. So if xy is a point in your parent function, then now we're going to get x over b comma y. And so an example of what does a horizontal stretch or a horizontal compression look like? Well, if I try to take this original shape here that I did up above, and now in red, a horizontal stretch would end up looking kind of like that. That would be a horizontal stretch. All right, so there is your homework, and enjoy, and we'll see you in class.